section, where it says 3.1 review, I'll just go over what the answers should be, and then if you have a question, please let me know. Question number 1 asks you to explain the difference between AQ and L. And I just wanted to make sure that everybody was clear that AQ means a solution. For basically every scenario that we would do in Science 10, it means I dissolved something in water. The L means it's a liquid. I didn't have to add water. It was already a liquid the way that it was. And I just want to point out, just one more time, those are some common substances that are liquids. Water is a liquid. Bromine, when it's alone, is a liquid, and so is mercury. Bromine and mercury are the only two pink ones on your periodic table. And remember, pink means liquid. Now, 2 asks you the law of conservation of mass. If I had to sum it up, I would sum it up by saying the reactants and the products have to be equal in terms of their mass. You have to have the same amount on the reactant side as you do on the product side. Now, the other questions here had to do with some actual, whoa, that was crazy, had to do with some actual numbers. So, for example, in question number 3, it said that in a sample of carbon dioxide that weighed 20.2 grams, if 5.5 of it were carbon, how much of it was oxygen? So all I need to do is subtract. 20.2 is the total. 5.5, we're going to say, was what the carbon represented. So that means 14.7 grams of it should be oxygen. So we're just trying to get you to recognize the idea that the total mass that you have has to be the mass of all of the elements individually. In question number 4, it's the same sort of idea. I have a total of 100 grams. If 40 of it is carbon and 53 of it is oxygen, how much is hydrogen? Well, I'm going to do a subtraction. 100 minus 40 minus 53.3. In essence, I'm doing 100 minus 93.3. What's left? 6.7 grams. So both of those questions are to try to illustrate that I have to make my total out of the atoms that are there. There can't be extra atoms, there can't be missing atoms. They all have to be accounted for. Does anyone have questions about 3 or 4 that they want to ask? So then question number 5, where I did notice a few people had some questions yesterday when you were working on it. It tells you that you have 50 grams of iron and 100 grams of sulfur that are mixed together. And my product weighs 107.4 grams. And then it says all of the iron reacted, but there was some excess sulfur, and that excess sulfur burned off. So A is asking what mass of sulfur chemically combined or actually reacted, and B asks how much of that sulfur burned off. So I know I had 100 grams of sulfur altogether, so I know that A and B together have to add up to 100 grams. I also know that my product should have 50 grams of iron in it because it said all of the iron reacted. That means that in A, there must have been 57.4 grams of sulfur. That would make up the rest of the total of the mass of my product. That means that for B, if I already used 57.4 grams of sulfur and I had 100 to start with, I should have 42.6 grams that burned. Would anybody like to ask any questions about anything in that first section, numbers 1 through 5? All right, so we'll get on to the balancing, and when we're going through the balancing, I'm going to tell you the strategy that I used for each of the questions. Just come down a little bit. There we go. So in 6a, and this would be true anytime I'm balancing, the first thing I think about is where is the biggest subscript? That's always the place that I want to try to start. And the logic behind that is, if I balance the bigger ones first, sometimes I end up balancing the smaller ones just by doing that. It's not incorrect to start with something that doesn't have the biggest subscript. It just might mean that it takes you a bit longer. So in this question, the first thing I'm going to do is just indicate to myself how many of everything I have, so that I can tell what I have the most of. So on the left, on the reactant side, I have 2 nitrogens, 2 hydrogens. On the right, I have 1 nitrogen and 3 hydrogens. The biggest subscript is this number 3. So that's where I'm going to focus to start with. I'm going to compare just the hydrogen. Whoops, that was weird. I'm going to compare just the hydrogen on this side and on that side. Now on the right, I have 3, and on the left, I have 2. And so the next step in the strategy is to find the lowest common multiple. This is what I showed you yesterday. So if I'm comparing 2 and 3, the lowest common multiple, meaning the smallest number that I can divide by both 2 and 3, is 6. So I would like for there to be 6 hydrogens on both sides of the equation. That means that on the left, for me to have 6, I need to multiply by 3. What in the world is happening here? There we go. To give me 6. So I put a big number 3 as a coefficient in front of hydrogen. On the right side, I already have 3. So to get 6, I need to multiply by 2. I put a big number 2 in front of NH3. Now I have 6 hydrogens on both sides. It's the same number. That's my goal. Now this number 2 that I added doesn't just apply to hydrogen. It applies to the whole compound. So instead of 1 nitrogen, I actually have 2 now because I added that coefficient. And you'll see that that actually made nitrogen be balanced without even me really trying. So now I have 2 ends here and 2 ends there. This is the balanced reaction. No coefficient for the first one, a 3 for the second, and a 2 for the third substance. Does anybody have any questions that they want to ask about the steps that you use when you're balancing? All right. So in the second example, that's a little bit trickier, I'm going to show you something that you can use to make your life a little bit easier. In the second example, you'll notice that hydrogen shows up in 2 spots on the same side of the reaction. When that happens, and you have something that's in more than one spot on one side of the reaction, try to do that one last. Now in this particular reaction, you'll see that you kind of have to do that because most of the other things are balanced. If I count, I have 1 calcium, 2 carbons, 2 hydrogens, 1 oxygen, 1 calcium, and then over here, this little number 2 applies to both things that are in the brackets. So that means I have 2 oxygens and 2 hydrogens, 2 carbons, 2 hydrogens. Since I have hydrogen in more than one spot, I combine and say that I actually have 4 hydrogens total. So I always want to take a look at what do I have in total on each side of the reaction. Now since I said if something shows up in more than one spot on one side of the reaction, do it last, I'm not going to look at hydrogen first, even though it's the biggest number. I'm going to look at the other substances. So if I look at calcium, 1 and 1, that's balanced. Same thing with carbon, 2 here, 2 there. That's balanced. But when I look at oxygen, I can see right away There's 1 here, but there are 2 there. So for me to make oxygen be balanced, I ask myself, what's the lowest common multiple? When one of the numbers is 1, it's a lot easier. It's the bigger number. So here the lowest common multiple is 2. I have 2 oxygens on the product side, but only 1 on the reactant side. So my strategy would be to put a 2 in front of the water molecule. Doing that means that now I have 2 oxygens, but it also means that now I have 4 hydrogens. And if you look, that just balanced my whole reaction for me. So I didn't have to worry about looking at hydrogen in both of the compounds at the end and trying to add them up and balance them that way. I balanced all the other molecules first, and in doing so, I made hydrogen be balanced. Does anyone have questions about B that they'd like to ask? So then in C, same process. We'll start with the biggest number. If I take a look and I write down how many I have of each thing, I see right away that Cl, chlorine, has 4. So I'm going to start by looking at the chlorine atoms. There are 4 on the left and only 1 on the right. So my strategy will be to put a number 4 in front of that molecule on the right. That means that now I have 4 hydrogens and 4 chlorines. Now that's good. It helped me balance out chlorine. Now I need to take a look at the other molecules. I have 4 hydrogens here, but only 2 hydrogens there. That's not the same. What's the lowest common multiple of 2 and 4? Well, the answer is 4, the bigger number. So I put a 2 in front of my molecule of water. Now there are 4 hydrogens and 2 oxygens. Doing that just made my whole reaction balanced. I count at the end. I have 1 silicon here and 1 silicon there, 4 chlorines on each side, 4 hydrogens on each side, and 2 waters. So you're going to use the same process every time. Start by finding the biggest subscript. Find the lowest common multiple and use coefficients so that you have that amount on both sides. Then you go to the next atom and you do the same thing. I'd like to recommend that at the end you do a little check. What I just did where I counted at the end how many do I have, just to make sure that I really do have the same number of each atom at the end of every question. Now the last one here, D, has a special little scenario that I'd like to show you a trick for. If I take a look at this, I have some polyatomic ions. PO4 shows up on both sides of the reaction. PO4 is a polyatomic ion. It's the phosphate ion. The same thing is true for SO4. It shows up on both sides. If you have this special scenario where you have polyatomic ions that stay intact, they're there at the beginning and they're also there at the end, you could consider a polyatomic ion as one thing. So I'll show you what I mean. Instead of counting all of the oxygens, which would be very cumbersome, there's lots of them and they're all over the place, I'm going to say that I have 3 hydrogens and 1 phosphate. Here I have 1 calcium and 1 sulfate. Here I have 3 calciums and 2 phosphates. Here I have 2 hydrogens and 1 sulfate. So I'm counting SO4 as one piece, one chunk. And I can do that because it's a polyatomic ion, and I know that they stay together. They're all one thing. So when I balance this, instead of having huge numbers like 8s, I have much smaller, more reasonable numbers. The biggest number I see is a 3, and so I could start either with hydrogen or with calcium. If you have 2 things that have the same number, there's no good way to tell you which one to pick first. I'll start with hydrogen because it's the first one going left to right. There are 3 hydrogens here and only 2 hydrogens on the product side. The lowest common multiple of 3 and 2 is 6, like we saw before. So I'd like for there to be 6. So I know that I have to do these multiplications. If I had 3 and I want 6, I have to multiply by 2. So I will add a big number 2 as a coefficient. At the end, I had 2, so to get 6, I add the coefficient 3. Now I have 6 hydrogens on both sides, but I've also changed some other numbers. I now have 2 phosphates here, and I now have 3 sulfates over there. You'll see that that was very useful because it just helped me balance a few more things. Now if I check phosphate, there's 2 here and 2 there. That's balanced. If I check the next one on my list, calcium, there is 1 calcium here and 3 there. 1 times 3 gives 3. So I add a coefficient 3. Now I have 3 calciums on the left to go with my 3 calciums on the right. And that number 3 also multiplied my sulfates. So the coefficients that I just added have now balanced the whole reaction. I have 6 hydrogens on either side. I have 2 copies of PO4, 3 calciums, and 3 sulfates. So I have the same amount of everything on both sides. So if polyatomic ions are present and they're there on both sides of the reaction, consider them as one thing and it will make your counting a little bit easier. Now that was the first question where you had to do some balancing. Does anyone have any questions they'd like to ask about number 6 that we've gone over? So number 7 was just an information question. We'll scroll down. Number 7 asks you, using the reaction that was there, to explain the terms that you see in the question. So this is really just a vocabulary question. I would hope that you could recognize that these are the reactants, and these are the products. So reactants always on the left, products always on the right. These little letters are the state symbols. So for example, zinc is a solid, but HCl has AQ, which means I have a solution. Hydrogen has a G, which means gas. Formulas would be like this part, ZnCl2. The formula shows you which elements do I have and in what ratio. A coefficient is like that big number 2. So am I going to ask you on a test, what's the definition of a coefficient? No, but I'm going to use the word coefficient. So I might ask you, what are the coefficients that you add in this question? And if you don't know what that word means, you're hooped. So the idea is that you can recognize in an actual reaction what each of those terms is referring to, so that if I asked you a question about the reactants or about the coefficients, you know which part I'm actually talking about. Does anyone have any questions about the vocabulary that's there? So number 8 is another balancing question. So we're going to follow the same procedure in number 8 as we did in number 6, where we look for the biggest number. We ask ourselves, what's the lowest common multiple? And then we repeat that for every single atom that's in our reaction until we have the same number of each atom on both sides. So we'll just go down a little bit so we can see all of them. So here's what I'd like to do. I think that for most people, towards number 8 and number 9 is kind of where you got stuck, if you were getting stuck. Some people I know finished a lot of questions all the way through here. But what I think I'd like to do is, while I'm here and I could answer questions, give you a chance to repeat or to finish parts of number 8 and number 9 that you struggled with earlier. So perhaps now that you've seen a few more examples, it might be a little bit easier for you to follow through with these. I'm just going to make a couple of comments because I made them earlier. For something like C, You have oxygen in more than one place on both sides of the reaction. So my suggestion here is do oxygen last. In this question and this one, you have polyatomic ions. Try to treat polyatomic ions as if they are one piece instead of separate atoms, and it might make your counting job a little bit easier. A and B don't have anything really particularly special about them. They're just finding lowest common multiples. So with those ideas in mind, I'd like for you to try looking at number 8 again. In terms of number 9, the first thing that you need to do is write the skeleton equation. That means write out all of the formulas and then worry about balancing afterwards. So in number 9, the first thing you need to do is take each word and make a formula out of it. So the first thing I would do, for example, in 9A, is write down the chemical formulas that go with each of those words. After I do that, I would worry about balancing. Now in number 9, let's not worry too much about the states that things are in. There's not a lot of clues in number 9, and I don't want that to be your focus. I want your focus to be, can I write the correct formula? And after I've done that, can I make sure I have the same number of each atom on both sides?